Okay, welcome to Year 13 Integration. And the way I'm going to start this topic is we're first going to look at what integration is and then allow our differentiation knowledge to get some base integrals. So just to remind you, to get from f of x to its derivative function, we use differentiation. So I've just finished my topic on differentiation, so there's lots of videos on my channel on that. But if we want to go from the derivative function back to the original function, then we use the inverse process, which is integration. So integration is the opposite of differentiation. So I'm going to use that premise to start with some basic integrals. So we've got some new base integrals, and what I've got here is a column of some functions, and then a column of their derivatives, and then we're going to use this knowledge to calculate some base integrals. So, for example, looking at the year 12 case, ax to the power n, when we differentiated it, we multiplied by the power, and then we subtracted 1 from the power. So if you reverse that, you add 1 to the power, and then divide by the new power. So we're going to add 1 to the power, so that's going to become n plus 1. I'm going to divide by the new power, so it's divided by n plus 1. And this is true for n not equal to negative 1. Because if it's negative 1, then we would end up dividing by 0. So we can't do that for negative 1. And we'll have a look at that case in a little bit. Okay. When we have an exponential, that's ae to the power kx, it's a natural exponential function, ae to the kx. When we differentiate, the multiplier of x will come down as a multiple, and the exponent of e will remain the exponent, that doesn't change. So when we're going to reverse that process, we want to go from here back to here again, we're going to divide by k instead of timesing by k. So if we have ae to the kx, when we integrate it, we're going to get a over k times e to the kx. And what I should have written up here as well was we have this constant of integration plus c. Okay, so if we are here and we differentiate a sine function, we get a cosine function. So that tells us that if we integrate a cosine function, we will get back to a sine function. So this knowledge here, from here to here, is going to dictate what goes in this box here, because we are now integrating the cosine function to go backwards. So we differentiated the sine function, we times by the coefficient of x inside the function. Well, to go back the other way, then we must therefore divide by the coefficient of x. So it's going to be a over k times the sine of kx. So we've divided by the coefficient of x, which is k, and this is dictated how we integrate the cosine function. So to fill this box in, we need to look at this line, how we differentiate the cosine, we get to sine, so therefore if we integrate sine, we're going to get back to cosine. So that's going to tell us what goes in here. So we've got a negative kicking around, so we're going to have a negative. Oh, don't forget the plus c again. Don't forget the negative. And just like we had with the sine, we're going to end up dividing by the coefficient of x. So it's going to be negative a over k times the cosine of kx. And of course, don't forget the constant of integration, which I've already done twice. Okay, the next one that we had in the differentiation was a log of kx. That differentiates to a over x. Well, we have no logs in our differentiation column, so we do not know yet how to integrate the logarithm function. So I'm going to leave that blank, and we're going to come back to that a little bit later on in the course. And then finally, this one here, we've got ab to the x. And when we differentiated, we just times by the natural log of the base of the exponent. So therefore, to integrate, we're going to divide by it. Notice the b to the x to b to the x. That's the same. It remains in the answer. So therefore, we can use this line to integrate. And we end up with a divided by the natural log of b times b to the x plus c. There's one other one that I want to put in here to allow us to integrate, and that is actually related to this. We can differentiate ax to the n for any n, but you cannot integrate ax to the n when n is negative 1. But if we look here, we have an x to the negative 1 in our differentiated column. So we should be able to use this line to integrate this when n is minus 1. So I'm going to write this here. That's going to give me a over x. And because that differentiated to that, then that must integrate to that. So that's going to give us, I'm going to write this as a times the natural log of x plus c. And the k here was actually a plus c. So you could put a log kx in there. But it's more standard procedure to put it as a log x plus c. We could fill out this entrant here, but we don't necessarily need to because it is actually covered by this one. It's just a special case of this when n is minus 1. So we end up with minus ax to the minus 2. But that is already covered by this one. Okay, so we have now 1, 2, 3, 4, 5, 6 standard integrals. You should commit these to memory. These are very standard, and we'll be using these throughout the rest of the integration course. Thank you.